Okay. This lecture is about multiple comparisons. Imagine an experiment where we have more than two groups. In this case, we'll do three groups. Groups A, B, and C. We have a continuous response. And we did an ANOVA, and the p-value of that is 0.01. So we rejected the null hypothesis, and the only thing we know now is that one of these groups is different. So maybe our experiment looks something like this. And the question is, how do we know which group was different? We can't say at this point. This p-value is called the experiment-wise p-value. What this chapter is about, multiple comparisons, is comparing group A to B, B to C, and A to C, and understanding which of these groups is different from each other. Now, the reason we did ANOVA and not just a number of t-tests is that each test we do has an error rate of 0.05. Type 1 error rate of 0.05. So we could possibly do 3 tests, and so we add those up. If we were to just do 3 different t-tests, our error rate would be 0.15. Okay? So the question is, how can we look for this difference and not have such a high error rate? There's 2 ways we can do this. One is we can have a priori tests. These are tests that are done before we even do an experiment. We also call these orthogonal contrasts. Okay. So, for example, if we did an experiment where we had control, low, medium, and high doses of a drug, we might want to know, is the control different from any levels of the drug? Okay, so we can ask that question. We might want to know if medium and high differ from low in the controls. We would have to ask that before we even did the experiment. Then we have another class of tests called post hoc tests. What post hoc means after the fact. Okay, so you did the ANOVA, you end up with a significant result, and now you want to know which ones are different. So these are done after a priori are asked before. And the difference is the a priori tests, you do not need to have significant results. So, in other words, if you do an experiment and your experiment-wise p-value is 0.06, he can still move ahead and test certain hypotheses. Because remember what an ANOVA does, it tests with a certain power, statistical power, if any one of these. But with orthogonal contrast, you could actually group these results and compare them to these results. And that test may have more power than just a regular ANOVA test. And then you can discover if there's some underlying structure here that wasn't evident with an ANOVA. For a post hoc test, you do need a significant result. So you do need a p less than 0.05, experiment-wise, result to move forward. Okay, if you end up with p greater than 0.05, if that's your alpha, your accepted alpha. If you end up with a p greater than 0.05, then you can't move forward. Okay. The first set of tests we're going to use for multiple comparisons is orthogonal contrast. Again, these are a priori tests. They must be asked before you do the experiment and can be run regardless of the experiment-wise p-values. The way to think about orthogonal contrast and what orthogonal contrast means is that the questions you're asking about your data are independent from each other. Now let's say we have groups A, B, C, and D. So these are our groups, and let's say this is, we're looking at a drug, and this is control, low, medium, and high. So let's say control, low, medium, and high. We can ask one question. And that one question right now is, let's compare control versus these other three combined. Here are some of the rules of orthogonal contrast. For any one test, the sums of the numbers you assign, and the sums will be coefficients. So we're going to assign these things coefficients. They must add to 0. And the contrast, maybe just good to continue with an example. So we're comparing this one to these three. And to get those things to be 0, we can do something like we can assign control -3 and these all 1s. So when we add these together, -3 plus 3 equals 0. Okay, the other rule, if we're going to ask another question, that question has to be independent of the question we just asked. And the cross products of the coefficients must, again, sum to 0. Bit confusing. Again, let's go by an example. So let's say we want to compare control versus high. Okay, so for any one question, the coefficients add to 0. So this one's straightforward. So we'll have -1 and 1 because we're going to contrast this versus this. Okay, that equals 0. Okay, but are these questions, these two questions, question 1 and question 2, are these independent questions? Well, the cross products have to add to 0. So -3 times -1 is 3, and 1 times 1 is, now we add these, we get 4. Okay, so we cannot do question 3, because that question is already embedded within this one. Okay. Now let's say, let's compare medium versus high dose. Okay, let's cross this out. And if we want medium versus high, we know that has to add up to 0. So we can just assign our coefficients. That equals 0. Now, can we ask that question? Okay. In addition to asking this question. So let's multiply it out. We got 1 times 1 is 1. 1 times negative 1 is negative 1. We add those together, we get 0. So we can ask, this is actually question 3. So we can ask question 1 and question 3. Let's clear this up again. A, B, C, D. And originally we asked controls versus the others. Now let's say we want to know if these two differed, these two groups, so controls and low doses versus medium and high dose. How would you set that up? Okay, we could do -1, -1, 1, 1. Okay, added together should be 0, that equals 0. But are these independent questions? So we have 3, -1, 1, 1, and that is equal to 3, -1 is 2, 3, 4, 4. So we cannot ask this question as well. Okay? And there's orthogonal contrasts. What this may seem complicated, but R actually does them for you. What you have to understand about when R does it is it compares a baseline to the other values, and you may have to rearrange the baseline, and I'll show you how to do that soon. Okay. For post hoc tests, again, these are questions you can ask about your groups after you run them. A common one you'll see is a Bonferroni test. Bonferroni tests, or correction rather, is you do what is essentially like a t-test. Okay? But instead of using 0.05 each test, you take your alpha and divide that by the number of comparisons. Okay. So if you had groups A, B, C, you have 3 comparisons. Okay, so your Bonferroni adjustment would be okay, 0. So now you do your 3 t-tests, and now you look for a p-value that is below 0.015. This tends to be very conservative. And that means you're making many type 2 errors. Okay? So a lot of people do not like the Bonferroni corrections because it tends to be overly conservative, and you are not discovering some true differences among groups. There's a number of other comparisons that are available. These include Tukey's, honest, significant difference, just called Tukey's HSD. And then there's Fisher's. Guess who's that named after? And his is called Fisher's least significant difference, Fisher's LSD. Hard to forget that one. Tukey's seems to be preferred among many biostatisticians, and that formula is Q times the square root of 1 over group, the size of group 1. So these are like the degrees of freedom. 1 over the sample size of group 2 times the mean square errors, okay, where Q is the studentized range statistic, okay? And what that means is if we look at two means and we're comparing these two means, the studentized range statistics would be essentially the standardized distance between the errors in the means of each group, okay? And again, with R, it's very easily done. We don't need to do any of these calculations. So Fisher's LSD is also used, but not very commonly. Okay, for multiple comparisons, how do we communicate our results? One way, if we have our 3 groups, A, B, C, actually let's start over again. Let's do this so it's a little bit less confusing. Let's say we have control, low, medium dose, high dose. And we have these responses. Okay, so we do our box plots like we would any ANOVA. And let's say that using Tukey's HSD, these two things are different. In fact, our controls were different from all the other groups. We always assign the first group A. Okay? And since none of these other groups are the same as that, they can remain separate letters. Your second one, you can go ahead and mark B, and let's say that low and high dose were similar. So these groups did not have significant different results according to the Tukey. Now, low and medium differed, but medium and high does not differ, okay? So we can assign this C to denote that these two means are not the same, but these two means are the same, so we can add a C to this. So this pattern indicates the results of 2P's HSD. And just to review, the control was different from everyone else. Lows were different from controls, and medium, but not different from high. Medium was different from controls and low, but not significantly different from high. Okay. Another way you'll see this is, let's put our data back up. Okay. Is with lines. So we put a line that doesn't overlap. We put a line here and here. And this same level means they're at the same level. This level here indicates that it doesn't overlap. And then these two, we can indicate like this. And a connection, okay, and at the same level indicates that these are the same. Okay, and if we were to use letters, it would be A, B, and B, and C, and C.